Yeah, you only count one quadrant and then everything else just gets reflected. So the signals are just going to be the ones from that one quadrant. So does anyone want to come up and count the signals? Actually, there's no whiteboard. Yeah, you can just point to it.
You have stickers, right?
I do have stickers.
Okay, so like this one, 1, 2, this would be 3,
Yeah.
and that would 1, 2, 3, 4.
Yeah. Those are all your 4 signals. Here, you can take one of the lame ones or you can take a gold star. So these 4 hydrogens are all unique. So they're all going to be different signals. So you have 4 total signals. Great. Now the next question is asking for the same thing. It's asking for how many different signals you have in the HNMR. So where do we start with this one? What was number 2? Yeah, 4. So for this one, do we notice anything interesting, any functional groups? Yeah. No problem. So for number 2, there's only 4 signals because there's 2 axes of symmetry. There's the one vertical one like this, and then one horizontal one like this. When we have symmetry, we can only count one side and it gets reflected. So since there's 2 axes of symmetry, we just need to take the signals from one quadrant and like reflect it around all 4 other quadrants. Yeah. That's why we always look for symmetry first with signal counting. The bottom right, like this one? Yeah. No, because it's the exact same as this one. Okay. So for this one, anything interesting? Yeah, we have a double bond. What does it mean when we have a double bond? Like what possibilities does that allow? Yeah, chemical shifts, but we're counting signals. So something with just a number of signals.
There's more than one proton on a terminal.
Yeah, we can have distereotopic protons. Is that the case in this molecule?
Yes.
Distereotopic protons? Yeah, there's no distereotopic ones. So the ones on the end of the double bond are just going to be normal, but they're counted differently. And what about this? What functional group is this? A ketone. It's just going to be an ether because we have hydrocarbons on this side. Remember, if we had a ketone, it would look like CO because the carbon bonded to the oxygen would have no hydrogens on it. So this is just an ether. It's good to just draw it out expanded. So now, does anyone want to come up and count all the signals? Or a sticker? Just point to it. There's like markers if you want to redraw the whole thing. But yeah, so there's 6 total signals. There you go. So we have 1 on the methyl of the ether, 1 on each side of the double bond, and then these rest of the aliphatic carbons just have their own unique signal. So we have 6 total signals, right? That makes sense? Okay, so for this one, we're going from signals to molecule instead of the opposite way. So we're given 2 signals, a triplet and a quartet. right off the bat, looking at the answer choices and looking at the signals, what can we infer? Yeah, there's going to be symmetry because this is a very low number of signals for the size of these molecules. So now what else do we notice that's going to help us answer? Yeah, we can look at the chemical shift. And what does a chemical shift tell us? Yeah, so we know we have some aliphatic carbons or hydrogens. And then this tells us we have something either next to a ketone or low heteroatom. And in all the answer choices, we have a nitrogen, so we know that this is just going to correspond to the nitrogen signal. They all have like carbon substituents that would give you an aliphatic signal, but you can just eliminate based on the symmetry. So for the first one, we only have symmetry down this way, right? And then all of these would be like 3 different signals, plus this one. That's 4 signals. That's way too many, so it can't be A. For B, we can just do the same thing, right? There's no axis of symmetry within this thing. So all these carbons are just going to be their own signal. So it can't be B either, because that's way too many signals. For C, what do we have? We have a nitrogen and 3 identical groups coming out of it. And then what do we have for D? Symmetry or no? So it can't be D. So that leaves C. And then if we think about it, it's the 3 identical ethyls coming out of the nitrogen. The carbon right next to the nitrogen will be the 2.4 quartet. And then the methyl all the way down here is going to be the 0.9 triplet. That checks out, doesn't it? So it's just going to be C. So that's how you should really approach these like signal to molecule questions. You just find unique signals that give it away and then start eliminating. And now we're going to use an actual spectrum to match a molecule. So how do you guys typically approach these kinds of questions? You start counting the signals? Yeah, that's definitely a really good way to approach them. I don't, because it takes me a really long time to count signals. It's kind of embarrassing. So I just do it my way. And I usually count signals at the end to confirm I got the right thing. But why don't we start this one by counting the signals? So how many signals are on the spectrum? Yeah. And knowing that there's 4 signals, which of these can we eliminate? The last 2. We can eliminate this one because it's only gonna have 2 signals. And then the last one, how many does it have? Yeah, it has a little more than 5. Yeah. It's what? Were these 2 are distereotopic? Yeah, so it's 6. Well, even if it was 5, it was already too many to match the spectrum, so we can just get rid of it. Now, what about the rest? Do they all have 4 signals? Are you sure? Yeah, the third one is also distereotopic. It's gonna have 5. So now we're left between A and B. How do we decide what the right answer is? Yeah, you can test with the integration. So how'd you go about doing that? Yeah, I would start looking at the chemical shift and then assigning signals based on that. So I'd look at like what's the most deshielded signal and then see if that matches up. Oh, you mean this hydrogen? Okay, so if we had this, well, if A was the answer, then what would this hydrogen show up as on the spectrum? It would show up as a singlet, and what about the chemical shift? It would be really high because this whole functional group is an aldehyde. And I missed that while we were doing this. So this whole thing is an aldehyde. And do we see an aldehyde peak on the spectrum at all? So it can't be A. And we eliminated everything else based on the number of signals, so it has to be B. So the way I did this one was I looked at the spectrum and I saw that there was a CH3 singlet, and then I looked in the answer choices. But I'd like to pick out like a peak that looks weird or that could eliminate a lot of the answer choices. So in this one, I chose the CH3 singlet, and the only answer choices with a CH3 singlet would be A and B. Then I looked at A and B. I saw that A was an aldehyde, and there was no aldehyde signal on the spectrum, so it couldn't be A. It had to be B. And I know sometimes, well, he really likes throwing these on your test, so it's good to like get through them quickly. That just comes with practice, which is why we're doing this.
You quickly go over which signal corresponds to which group of protons?
Yeah, I can. So we know that this CH3 corresponds to this singlet up here. And then what about our double bond protons? We have one up here. What would the multiplicity of that be?
Oh, multiplicity.
Yeah.
Would be a doublet.
It would be a doublet. And then in the double bond region, we have a doublet and a multiplet. It's not gonna be the multiplet, so it has to be the doublet. This one, since we already eliminated one of the double bond region signals, we know this one's just gonna be the other. Let me just change the color. And then we have a CH3 doublet all the way at that. So for the next one, where would you guys start? The signals on the spectrum or counting the signals on the molecule? Okay, that works. So sure, let's just count the signals. There's 5 signals on the spectrum. What about each of the molecules? The first one has 6. Yeah, that's too many, right? So we get rid of A. What about B? That one does have 5, so we can keep it in. And C? So we also keep C in. And D has, so D goes away. And the last one. So we can keep the last one. But from the last one, we see that we have a carboxylic acid. And what would the chemical shift of this proton be if it was on the spectrum? It would be like all the way up at 12. And there's no peak in that region at all, so it can't be the last one. So now we're stuck between B and C. So how would you differentiate between the two choices? You mean the methyl at the end? Do you want to come up and,
Since it's having an O, you can't really like count the neighbors. It's just the plus one.
so this one would be a singlet.
Mhm.
And then you're saying this one would not be a singlet.
Yeah.
Yeah, that's good. And then the other thing to notice with that is that this methyl is right next to a heteroatom. So the chemical shift would be way higher than this one, right? So on the spectrum, we see that we do have a methyl signal. But what chemical shift is the methyl signal at? It's at 2. Is that high enough to be right next to an oxygen? It's not. But we do have a methyl singlet right next to the ketone. Does that check out? Yeah, so it's going to be B. And you could check the rest of the signals with their multiplicity and integration. So now we move on to another one. And do you want to start with counting signals again? So there's 4 signals in the spectrum. So what can we eliminate from the answer choices that doesn't have 4 signals? Wait, no, yeah, A is 4.
Yeah.
5. Yeah, I'm not exactly sure. So we can just keep it in for now. Yeah, the thing is that this is quaternary, so I'm not sure if it would work the same way. Although I think it would, but just to be safe, we will not count it. Does C have 3 signals? Yeah. So C goes away. For which one?
Oh, because they're, I see.
So C, D, and E all have 4 signals. Okay, so which ones are we keeping in? All right, we can keep in A and B, and the rest, I'll trust you to get rid of them. So between A and B, how do we differentiate? Yeah, you can look at the chemical shift. So what signals chemical shift would you look at? Yeah. You could do that one. I think a easier one would be the 6H signal. I think that would be this one or this one. But we see that the 6H signal is around 3 ppm, which is the heteroatom region. So because it is that deshielded, we know that that isopropyl looking thing is going to be right next to the nitrogen. That's how I ended up with B.
Is B, or because it's not on a double bond?
Yeah,
Um,
it's going to be rotating around this bond.
we count the, bonds at the end as 1, 2, 3, 4.
What do you mean, like
Like
these?
the ends. Yeah, so that one, like one of them, where's the key pass? I can make sure I'm doing it right.
What am I counting?
The bonds for D, it says there's 4 signals.
like counting the signals.
Yeah, the signal.
Okay,
Yeah.
so you have one up here. They're the same symmetry, one down here, one here, and then the H of the aldehyde. So just from that isopropyl kind of signal, I figured that the only one with a de-shielded isopropyl would be answer choice B. So that's just what I went with. If we did A, this one is going to be in the aliphatic region. And this is way too close to 3 to be in the aliphatic range. So I got rid of A. So after getting between A and B, I picked a signal that would differentiate between them. So I picked this 6H signal, which usually means something that looks like an isopropyl. The isopropyl is slightly de-shielded around 3, which means it's in the heteroatom region. So it's right next to a heteroatom. And this one, the isopropyl looking thing would not be near 3. And B is the only one where you get that. Yeah.
I'm not sure aliphatic means. Can you just?
Oh, aliphatic just means like like hydrocarbon. So just CH, whatever.
And where is that from?
It's from like 0 to 2-ish, like 2.5.
Okay, thank you. I have a question. I was wondering if
The CHO, yeah, it would be a triplet because it's 3 bonds away. No, but they both have the triplet up here.
Oh, I just see that as one, sorry.
No, it's fine. It's kind of far. Did someone, you had a question?
A have 5 hydrogens in it.
Yeah, I don't know. I'm not entirely sure. So I used another method to get my answer.
So if we were to use the signal, we would automatically go out of
Yes, but I did not trust my signal counting, so we took the roundabout way. Okay. So for this one, we have 2 protons and we're comparing the relationship between them. So what is present already in this molecule? Anything cool?
Is there diastereomers?
Yeah, they are diastereomers because there's a chiral center. So we have a chiral center. If we have a chiral center already present and then another prochiral center, the hydrogens on the prochiral center are going to be distereotopic. They're going to be different signals. So if you have a molecule and you're counting signals on that molecule, you look to see if there's an already existing chiral center on there. So we do have a chiral center right here. And then its neighbor, the CH2, like if we replace one of these hydrogens with a heteroatom or something different, then this would also become a chiral center. So that's what we call prochiral. Because this chiral center exists and because this carbon is prochiral, these 2 protons are distereotopic. They're going to show up as different signals. And then the same thing with double bonds. Do you remember how to tell if double bond protons are distereotopic or not?
No. Yeah, let's give this
Okay, so if you have a double bond, so you have 2 terminal double bonds. Now, which of these 2 protons is going to be distereotopic and which is going to be homotopic? Yeah, why is it homotopic? Yeah, because there's symmetry. If we cut the double bond in half and look at what's on the other side of the double bond, if this group is symmetrical, then they're homotopic. And then what about this one? Yeah.
So this means that they're almost the same, there's one thing that changes.
Yeah. So they're almost looking at the same thing, but they're not. And for this one, there is no symmetry on the other side of the double bond. So are they going to be same or different signals? Yeah, they're different. Because if you look at one hydrogen, that gives you the E isomer, And then if you look at the other one, it gives you, well, this one gives you the E and this one gives you the Z. The point is, because they give you two different isomers, they're distereotopic. So I think that's enough NMR.
Oh, the one before was, you said homotopy?
Yeah, these are homotopic.
Do you have anything kind of on the?
No, but also J coupling is not that important for your test.
Okay.
Yeah,
Is that gonna like try to specify exam and do a big coupling in there?
I mean, maybe. He could do anything. J coupling is usually something they just throw in there for like your understanding. I don't have an example what a practice problem, like a real problem would be like for that. So I kind of I made these homemade practice problems for you guys because they go over basically all the reagents. So yeah, we have this multi-step synthesis and it covers a lot of stuff and it looks very homemade because it is. So does someone want to try it?
The whole thing.
Okay. Yeah, I mean, the whole thing or as much as you want. It's up to you. If you want.
Do the whole thing.
You can go on the other side of the board.
No, we're not allowed to.
Other side's better, so more people can see.
Oh, yeah, you got it.
I could, but like, I don't want to stand there and keep yanking it and it's not going up.
No, just leave it. That'll be on the whiteboard.
No, I know, I'm just saying the thing like doesn't go up when I pull it and I don't want to like just stand there and keep, yeah, yeah.
No, it's not.
So we're starting with a methanol and we have a PBr3. Yeah, you could do the mechanisms if you want.
You just wanted to like write.
Yeah, just write the final product.
I'm sorry.
I don't even know the mechanism for PBr3. That's like, I never bothered. Yeah, just write product A.
Oh, okay.
So every time we have an alcohol with the PBr3, what's the final product gonna look like? It's gonna answer it. Yeah.
Do we have to know the mechanism?
No.
We just got to know what happens.
Yeah.
Gotcha.
Yeah, that's exact. Wait,
Also the mechanism.
I think you have one too many carbons. So we're starting with a methanol, right? Yeah. So we started with a methanol. That's one carbon with an alcohol attached to it. When we add PBr3, all that happens is that the alcohol gets replaced by Br. Pyridine is just part of the mechanism.
Yeah, you just need to know.
No.
I think it's a byproduct. Pyridine will be deprotonating the intermediate species and then you get the.
What? Yeah, it's just a solvent as part of the reagents to get this final product.
It's just in it, right?
Yeah,
Okay.
just know it's in there to make the mechanism work. Yeah, So we have an alkyl bromide. We treat it with magnesium over ether. When you have an alkyl halide and magnesium over ether, what do we get?
Grignard.
Yes, we do get a Grignard. So what happens when we get a Grignard is just the Mg inserts itself in between the carbon and the bromine. So we just get a methane with an MgBr. So product B, yeah, he just wrote a methane with a negative charge.
No, so this is just getting you set up to do like another negative. Like he wrote it where it just has like.
When we see an alkyl group attached to an MgBr, what can we do?
It's like.
Yeah, we can just cross out this and then redraw it as, yeah, as a hydrocarbon with a charge. So that's what he drew up there.
That's like the carbonyl carbon, and then you form this species right here. which
Yeah.
would then be protonated by the acid, right?
Would it, so would it get protonated now? Is there anything else we can do with that lone pair? Huh?
Well, okay.
The one on the oxygen? So can we do anything else with it, or do we just have to protonate now? Like, can we do another addition on the thing you drew?
Right here?
Yeah. Yeah, like, could we reform a carbonyl to do another addition?
Oh, yeah, I see what you're saying, yeah.
No, we can't. That was a trick question.
Yeah.
Yeah, we can't, because there's no leaving
Yeah, of
groups.
course, yeah, I know. It'll be a form of charge, maybe one, that would not be a carbon.
Yes.
Anyways, I'm sorry, I was not.
No, it's fine.
understanding
It's
what you were
fine.
asking.
Don't worry.
So what was that?
You're just protonating it.
Yeah, but I carbonated, and then you get the secondary alcohol.
Primary or secondary?
I mean, I'm sorry, primary. That's right. Good, okay.
I'm sorry, so the product of B and DPR plus G.
No.
Yeah, it's an MgBr attached to CH3.
Yes.
Yeah, yes.
When we're looking at NaH negative underneath, do we just assume that there's something under there?
Yeah, usually it's gonna be like water to follow up the base.
Okay, because like that's what we found about today.
Yeah,
is
it's
we
just
assume it's
assumed.
gonna be carbonated. It's just an alcohol.
Oh, so we have alkoxide.
That will be attached to carbon to take out the bromine, and you get an
Yeah.
With this methyl ether. I mean,
Yeah, methyl,
methyl ether.
ethyl, or there's 3 carbons.
Yeah.
Propyl.
Propyl, I'm sorry, yeah, propyl, that's right,
Susan in his head.
Yeah. So you're right, the final product is methyl propyl ether.
So C was. So what's C?
I'm gonna go through everything, like right now. Don't worry.
I got C, but after C, what do you?
We'll go through all of them, A through E, no worries. Yes, that's perfect, thank you.
We got like 5 stickers.
Yeah, take as many stickers as you want. Okay, thank you.
Yeah.
So let's go over the whole thing. So we started with a methanol. We have an alcohol and we add a PBr3 to it. which just replaces the alcohol with the bromine. So we got to product A, which is just a methyl with a bromine attached to it. After that, we have an alkyl bromide. When we combine an alkyl bromide with Mg over ether, we get a Grignard. So all we do is just stick that Mg right in between the bromine and the carbon, and we get your Grignard reagent. Remember, when you see something with MgBr attached to it, you just cross out the MgBr and rewrite it as that thing with a negative charge. So now, what are the properties of a Grignard reagent? What does it act as in a reaction? It's going to act as a nucleophile if there's no acidic protons around. So in these reagents up here, what do you think the Grignard is going to attack? Yeah, so we have a carbonyl. Technically, it's called formaldehyde, but yeah. Yeah, exactly. So what we do care about is that we have a carbonyl and Grignards attack carbonyls. So the Grignard's going to go in, it's just going to do an attack like that up there on the board. And then you get product C. So the hydrogen stayed there. We just added this methyl from the Grignard reaction. And then the alcohol got protonated by this, even though that step might not be indicated every time. So cool, we have product C. And we get a primary alcohol. So now we react that alcohol with a strong base. And what does that give you? Water? Yeah, we just get ethoxide. So is ethoxide a good nucleophile? Yeah, it's a pretty good nucleophile. And good thing we have an alkyl halide for it to attack. So in the last step from D and E, you have an alkoxide, actually from C to E, you have an alkoxide and an alkyl bromide. What reaction is that? That's Williamson ether synthesis. So we know it's a Williamson ether synthesis. So what's the alkoxide going to do to the alkyl bromide? Yeah. And by what mechanism does it do that? SN2. You're so ready for exam. And then the final product, since we have an ethyl on this side, and then what is this? Yeah, it's 3 carbons, so it's a propyl. So our final product is called do we have 2 ethyls?
Oh, no.
Yeah, ethyl propyl ether. Because on one side we have an ethyl, on the other side we have a propyl. And it's an ether, so. So we already named the final product. And then I added signal counting to this just because. So let's count the signals just because. How many signals would show up in the NMR spectrum of ethyl propyl ether? Yeah, it would be 5, right? Because each carbon would just have its own signal. And we can skip the chemical shifts. We don't have a time for another one of those, so we'll just skip. Okay, we'll do this. So we have another relationship between proton sting. You have HA and HB. So what do we notice about HA and HB? They are diastereomers. They're diastereomers. Why? Because there's a double bond. And what about that double bond? Yeah, it's terminal. And what about the other side of the double bond? Yeah, there's no symmetry. So these two are going to be diastereomers.
Sorry, what is in the symbol?
Vicinal means like one carbon over. So if you like two things with a carbon bond in between them, so like this. There's like a bond length in between them, so they're vicinal.
Okay. So just the symbol bond is not.
No, it could be on a double bond too, as long as they're like that one bond length away.
Oh. So could they be vicinal and diastereomers?
No, the diastereotopic, all that is only for geminal protons. Geminal meaning coming from the same carbon.
Oh, okay.
Yeah, so all those only apply to geminal protons. All right, in the last 4 minutes, we'll start dabbling in chapter 11. So it's asking for the major product of this reaction. What do you think this reaction is? Yeah, and how do we know that? Yeah, so looking at the reagents, we can see it's a hydroboration oxidation. And what's the regioselectivity and stereochemistry of this reaction? It's net anti and yeah. So knowing that, what would the answer be? It would be, yeah. Because the alcohol is on the least substituted, and then it was a syn addition with the hydrogen. Who said that? You want a sticker? Yeah. All right, one more IUPAC one. So we have this molecule. What are our functional groups on it? And which one takes priority? So now how do we name this? What's the parent chain going to be? Yeah, it's a pentane, but it's a pentene because we have a double bond. And what are your substituents? So we have a methyl. Yeah. Yeah, so how would we put that all together? Yes. Yeah, that's right. So you can take a sticker for that, whoever said that. What a shame.
You're too good for stickers. I mean, if they don't want
All right, so that's all. I'll pull up the sign-in thing again in case you missed it. But yeah, and then we'll just finish up the practice problems on Thursday.